and they know they already hate them before they know what they are. But it's just a weird-ass choice of symbol. But, you know, same way I had to internalize what that meant. When I say square root of 9, you all know it's because you've internalized the question so much you don't have to think about it. But the question this asks is, what does it take 2 of, or what do I put a power of 2 on to have it come out to be 9? Well, 3. So here the unknown is the base. Here the unknown is the power. So the answer to a log is always a power. So the properties of logs are the properties of powers because logs are freaking powers, right? So when do I subtract powers? Yeah. So if I have like bases, when would I subtract their powers? When I was doing what with the things? Divide. Right? So you can rewrite that log equation as a single logarithm, and then somebody might be like, well, what the shit does that do for me? Well, if I had an equation like log base 7 of x equals 2, then of course, like you said, it's just another way to kind of rewrite the inverse of an exponential. So now I can rewrite this back in exponential form, and that would be what? 7 squared, and then I would know x is 49. Yay. So if I can make those 2 logs become 1, it becomes an equation just like this. You guys look skeptical?
2a, I think it was like 3, 5 log with the base 3 to 8.
Yeah, so I mean, once you put them together, you'll get something that looks maybe something like this. Right? Doesn't have to be like this. There were many different versions of the quiz, so everybody had this, but nobody had this. And then here I would just say 3 squared is all that shit. Multiply that up, it's algebra. Right? So, I mean, the idea of a log, what's log base 2 equals 3? How can I rewrite that? I didn't even tell you what's in here. 2 to the 3rd power equals whatever this is, even if it's a lot of things. Who cares? So log of this shit equals, okay, so 3 squared equals this business. And then I just algebra that boy up. Yes?
So if we like did it that way, what was like a way for us to like prove if we got the right answer?
You could plug it back in.
Literally just like, but I mean it's a log base 3. So I remember like, I mean in the calculator you only, it assumes log base 10, right?
Oh, I see. All right.
So
Then you have to remember change of base, or you have to know where your log base anything button is. Yeah. You guys remember something called change of base formula? A little bit? It's really easy because the base goes on the bottom. Right? So if I want to do log base 7 of 11 in the calculator, I can make that log 11 over log 7. Based on the bottom. Does that sound at all familiar? Okay. I didn't go that deep. I mean, that's kind of a deep cut. I went surface properties of logs. All right, so those are going to come up every now and again? Yeah.
So the only thing I forgot was that problem 2a. There's like 3 with...
Oh, okay. You're talking about... Okay. So, again, it was different for different versions of the quiz, but help me out here. How does log base 2 of x relate to 2 to the x? How do these relate? How does the cube root of x relate to x cubed? They are inverses of each other. Well, these are inverses of each other, aren't they? Right? If I know that the cube root of x is 2, I can rewrite that in this form, x is 2 cubed, right? I mean, that's... So isn't that the same thing I do with logarithms? Inverses are just different ways of writing, so if I have x cubed equals y, right? I can write that as x equals the cube root of y. I mean, it's just root form and power form, log form and power form. Same stupid idea. Why? Because they are inverses of each other. Is that, you guys semi with me? Okay. So let's see. Where was it? Oh, if these are inverses of each other, you're gonna love this shit. If I had 2 to the log base 2 of d, what do inverse functions do to each other? Yeah. So the answer is D. Right. I know. Add one extra little step. Now, so that's one idea you got to have to do this problem. The other idea is another property of logarithms. Actually, the most important freaking property of logarithms. So if I have something out front, something like that, how can I rewrite that?
Log base 7 times to the third.
There you go. Yeah. So if you had something here, it was in your way, get it out your way. Right? Okay. Anything else from that quiz, if it's still in your head? Some of you guys are like, I wiped it. I didn't want to think about it. Others of you are going to have nightmares or something. I don't know. We'll find out. All right. That's what I am. Nightmare fuel. All right. Hopefully the other ones weren't too horrible. The first problem, there was this problem basically exactly like that in the homework. The second one is just general stuff you should know. The third one, totally from the homework, right? And the fourth one was just, solving equations. Yeah. Okay, I like it. Now, some of this stuff I understand has been buried in the past. This is one reason why I did this, is to bring it back up. Yes?
You give partial credit.
Never. It takes too much time. Yes, I do. I totally do. Totally. I grade based on concept, so getting the right answer is nice. Applying the correct concept is more important, right? So if you make a mistake on step 1, you lose points for that mistake, but if you do every other step correct, you won't lose any more points. I always hated that you make a mistake on the first step, and then you get no chance. It doesn't matter what you knew after that. So for some teachers, you're like, I knew everything. I just forgot a negative. You're like, no, Jeff, it's all wrong. So I don't speak from experience at all. So yeah, I give partial credit. Hell yeah. Yeah. Otherwise, I just use Scantron, right? Which, if any math teacher uses Scantron, they are not a math teacher. I don't know what they are. Calling somebody. Is this even going? Yes, good. All right. So yeah, don't ask me if you need Scantron for my class, obviously. Anything else from the quiz? Did the rest of them go okay? That one problem, there was one where you could either factor it or you had to use quadratic formula. Yeah, okay. So I have this graded tomorrow. I did tell you guys that I was going to have another quiz tomorrow. And it was going to do 2-2, 2-3. If you want, I'm willing to push that to Monday if I also throw 2-4 on there.
That's a deal. That's a deal. Take that right now.
Okay, it sounds like sold. It sounds like that's. Some of you guys are like, no, but more of you are like, yeah, and. So how many want it on Monday, including 2-4? How many want to keep it tomorrow? I like it. Yeah, you're like me. Very often I'm the lone hand in the room, so it's okay. All right. So, that's so nice. So I have it Monday. It'll be 2-2, 2-3, and the epsilon delta 2-4 stuff. Okay. Last time we got most of the way through section 2.5. I think we made it basically all of the way. Any questions from homework stuff? Yes.
What's the squeeze theorem?
Ooh, yeah, cool. It's one of my favorite. All right, and you gotta love the name. Where did that first come up? I forget.
36. Question
In 2.5?
2-3.
2.3. Okay.
Yeah.
I couldn't remember where it was, and I knew I was gonna skip the poor little dude. Where did he even talk about it? All right, let me just show you what it is. So let me ask you that if f of x, g of x, h of x, all continuous around x equals a. So in some neighborhood of x equals a, they're continuous. And I know that this is true. F of x is always at most g of x, which is always at most h of x. If the limit as x goes to a of f of x equals the limit as x goes to a of h of x, what must the limit as x goes to a of g of x be? And let's say that this equals L. So what's this look like? What's this look like? Let's see. Here's a. Doesn't matter where a really is. Just going to throw it somewhere. Here's f. Weehaw! So that's f. And here's h. Now the limit is f as x approaches a of f is L. Is that cool? And it's continuous, so it actually gets there. You with me? Limit of h is also L. So here's h. Weehaw! Woo! But h has always got to be. Do I have these the right way around? No, of course I don't. We call this h. Turn my symbols around on myself. There we go. So f has always got to be below h. Is that cool? They're at most equal to each other, if not f below h. Is everybody with me so far? See why it's called the squeeze theorem. G is supposed to always be between those two. So what must the limit as x goes to a of g of x? It's always got to be between these two. Does it have any option to be anything else other than L? Can the limit be anything else if it's supposed to be between those two? All the options are squeezed away. I mean, it just gets squeezed in the middle there. Woo. So therefore, the limit as x goes to a of g of x has to also be L. All right? I like it. Maybe no. So I think for some reason I always think about that last scene of Terminator. Okay, so let's try. This is nice theorem picture. Yay, Jeff. Let's try an actual freaking problem out. I don't know. It doesn't matter. Find the limit as x goes to 0 of what you got, Jeff? Yeah. Let's do x squared sine x. What is x squared sine x? What is sine x always in between? Negative 1 to 1. I love it. Those are the natural boundaries of sine x. Is everybody cool with that? Okay. Is that the function I'm investigating? Is it? What function am I investigating? X squared sine of x. So how do I make that show up here? What do I do? How do I make that show up there? What do I do? What's missing here? And so what do I do to make it show up legally? What do I do to this? Multiply everything by x squared. Why is that allowed? Because x squared is always positive. It's not going to mess up with these, right? So this will be negative x squared less than or equal to x squared sine x. Let's see x squared. Now, is everybody cool with what I've done so far? Now apply the limit to everything. The limit as x goes to 0, negative x squared what's the limit as x goes to 0 of this? What is it? 0. What about this side? 0. Therefore, the limit as x goes to 0 of x squared sine of x has to also be 0. The only way to make that true is if the middle dude's limit is 0. If it was 1, it violates that. If it was less than 0, it would violate that. That's the squeeze part of it, right? The ceiling and the floor collapses, therefore I must be the same place they are. Right there, if I'm in that house. I'll be feeling too good.
So that's your answer.
Yeah, or so therefore,
Oh,
yeah, it should. This leads to therefore, the thing I just said.
okay.
Yep. Cool. That's the classic use of the squeeze theorem. It shows its head every now and again. The name sounds like they just ask me, what do you want to call this? Oh, squeeze. I like to squeeze. All right, too. Stay away from it. Is that all right? If you want better pictures, let's see. Where they first do use squeeze theorem. I can't remember the first place it shows up. You said that was in section 2.4? 2.3. Okay. Squeeze, there you are, 101. Oh, there it is, right there. Page 101 is the third theorem. You have a better picture there, all colorful next to that. Same picture as that one. Okay, all right. Anything else from homework stuff? Okay, all right. We'll just keep going. The last thing we talked about was monks climbing mountains and stuff. It had to do with the intermediate value theorem. Let me throw this problem at you. Let's see what you think. Oh, what are you? Minus 20. Oh, you got a 2 there, not 20. Show that that function has a root between 1 and 2. This is obviously, hopefully, involved in the intermediate value theorem somehow. The intermediate value theorem is the one that said if you have output here and an output here of a continuous function, and there's some n in between there, is it possible for that not to be an output of this continuous function? Could I possibly have that not be an output? Another way to say that is there a way to connect these points without going through this line? No. So somewhere I've got to, man. So somewhere there's going to be that output. So how the hell does that relate to this? Well, what's it mean to be a root of something? The root of all evil. What's it mean to be the root of an equation? That's where the output is. Where's the ground? Where's the ground in this? Where would you say the ground is? The x-axis, right? So where should roots be? Starting at the x-axis, and so a root means the output is 0. That's x-intercepts. That's another way to say x-intercepts. That's another way to say the 0 of a function, right? So if I'm looking between 1 and 2, how would I possibly know for sure that this function has a root between there? What would force it to go through 0 somewhere in here? If one side it was, and the other side it was, there you go. So what's f of 2, and what's f of 1? You know, part of my heart is loving the fact that most of you guys haven't touched your calculator. It's kind of nifty. I don't know if you're actually doing this by hand, but I love that. That kicks ass. It's not that hard, right? Especially for 1. Holy shit. Not that hard. If you guys reach for your calculator immediately, that's all right. So for 1, it says 4 minus 6 is negative 2. Plus 3 is 1 minus 2 is negative 1. So that's negative. Where to put it?
12.
You get 12 for this one? So, so f of 1 is negative 1. F of 2 is 12. So I know it's going to go through, and more than likely it's going to probably be over here, because this is a relatively well-behaved function. But still, I mean, I could improve on this. How would looking at f of 1.5 improve this? If f of 1.5 is positive, that means that the root lies between 1 and 1.5. So the calculator algorithms actually use this idea in a modified way, but it basically uses this idea to zero in on the root. If you ever use that function in your calculator, it asks you for a left side, a right side, and a guess. The left side and right side narrows down where the answer could be, so then it can use a little, oh, there it is. Of course, it does it very quickly. So if you did this and got the answer, you could tell between what two values the root must be. What is f of 1.5? Anybody doing that? Maybe. Yes?
Good question. So since it's to the power of 3 for this problem, is it possible that multiple zeros lie in between?
Totally. So this, I think it just says that there is a root. So there could be more than one. I love it.
But then if you find out 1.5 and 1, there is also a chance that they're both between that in some scenarios?
Totally. Yeah, I mean, this is not the best way to find it, and this is not telling you how many there are. It's just a way of knowing that there's at least one. Yeah. Because you could have functions that go insane and they have billions of roots in there. I like it. Okay. All right. So that is one application of intermediate value theorem, is showing that there is a root between two things. So it gives us a area to search for it. Okay. How many of you guys have actually done that? I mean, on the calculator, actually found the root of a function. Maybe this is going to, all right, let's do this. So I want to, all right. So if you don't have your calculator with you, oh well, you just pay attention. Poor little dude. Let's touch. Go on, touch. Good. There. So real quick. We will eventually be using the calculator to do a few things. I need to make sure that you guys know how to use it to do certain things. To be honest, I'm a lot more old school The less you do in the calculator, the more you actually understand yourself. But the calculator is pretty good about getting something up there real quick so we can talk about concepts. So that part I'm fine with. Can somebody, thanks, man. Figure out which one of those is better. So let's put this sucker in there. 4x cubed. Where are we at? Minus 6x squared plus 3x minus 2. Okay. If you haven't really used this much, sorry. But if you hit zoom 6 whenever you put something new in, that's a decent place to start. That makes it standard window, negative 10 to 10, negative 10 to 10. What I feel pretty good about that, this is the whole thing. What should a cubic look like? Like this, right? I mean, this part in the middle might become up and down and up. It might become exaggerated depending on the coefficients of the parts. But it's going to have that going up and then that temporary resting point or even turning point and then going back up again. So I feel pretty good about this being everything. I'm curious about the area between 1 and 2. So let me show you something else that's kind of cool. Let me turn you around while I'm thinking about it. So people who are at home, oh, that's very far away. There we go. If you do zoom box, this feels like one of those stupid CSI shows. Enhance. So, because that's what every computer can do. So I can zoom in on the area I'm most curious about. So there's the root between 1 and 2. And now to make the calculator find it, I can sell it. Is everybody cool so far? Who's playing along? Are you guys good? So if I hit second trace to go to calc, everything up here is about graphing. So if I want to calculate something from a graph, I go to this calc here. And look at all this stuff. The last 2 things here are things we'll be learning this semester. So notice that, hey, I can do some shit on my calculator, yay. And I'll show you that later. It's all good because you got to show me work anyway. What was I doing? Oh yeah, I'm trying to find the root. So another name for that is the 0, because that's where the function's value is 0. And here it's going to ask you 3 questions, right? What is your quest? No, it's going to ask you left bound, so you go to the left of the answer, and you hit enter. Right bound, you go to the right, and you see what it's doing? It's kind of like making sure, it has a way to make sure that there's a sign change. Enter, and then give it a guess to give it a good spot to start the algorithm. Enter. Plop. 1.22, blah, blah, blah. So if I did that thing up there a few more times, if I knew it was between 1 and 1.5, then I'll do 1.25. And then it would be between 1 and 1.25, I can cut that in half. I can keep making it better and better and better approximation. And like I said, the calculator's algorithm uses that to an extent, a certain modified way. But watch, I'm going to do a mistake on purpose. I don't want you to see the error it gives me. So if I do this again, if I do find the 0, and I give it the left bound of this and the right bound of that, do you see how that's completely bullshit? And my guess is in there. It's going to go, you better do it, you silly. No sign change. That's the first thing the algorithm checks is, am I going to waste any processing power for this crazy human doing this shit to me? I'm not going to waste any computing power because there's no sign change. How could there possibly be a root in there? It just used intermediate value theorem. So I'm not even going to look. Is that cool? Okay. I like that error. It's beautiful. It goes right along with the idea. No sign change. Okay. Enough of that. While I have this up here, are there any questions real quick about stuff in the calculator while I have this up here? Okay. So there'll be really some cool stuff later this semester. We'll be doing, obviously, a lot by hand, but I'm going to show you how to check some of the stuff on the calculator, some of the calculus stuff we do.
You can do that for both x and y-intercept?
Well, y-intercept is beautiful. Let me go back to zoom 6. Y-intercept is nowhere near as difficult because the fact that this is y equals, that's the only kind of thing to see in graph, is meaning that I can plug stuff in for x directly. Plugging stuff in for y doesn't do shit for me, but how do you find the y-intercept? You make x 0. So to do that, I can see the answer is going to be -2. But to do it in the calculator, I would just go to calc value and tell it, what about x equals 0? And it says -2. I don't have to do any algorithm, any shit, right? Because y is already solved for. It's the x stuff that would be difficult to get. Maybe. Okay, I like it. So every now and again when we learn some more stuff, we'll throw the calculator stuff up here too. There will be a couple things that you'll need the calculator for, but for the most part, I'm going to show you how to check a lot of the work that we do on the calculator. We'll also use it to just graph things so we can talk about the graph quickly instead of having to do it all by hand like you already did in 176. But don't worry, you will be doing a lot of graphing by hand also, in case you're worried about that. You're like, that's not quite the right word. Okay. So that was the one last thing out of section 2.5 that we didn't cover directly, really. I want to get to 2.6 and then maybe talk a little bit about 2.7, and we should be heading out decently early today. We'll find out what happens. Okay. Wow. Okay. So, yes.
So the intermediate value theorem, we're just finding the zeros between 2 points, right?
One use of the theorem is to show that there is a 0 between two x values. That's one use of it. It's got a lot more general uses, right? It's sort of like when you first learn how to factor, the next immediate thing you do is solve equations like x squared minus 5x, you with me? Because that's the first immediate use of factoring. Is that the only use of factoring? We all know much better now that there's a freaking lot of uses of factoring, right? So that's like the first little example of what intermediate value theorem could be used for concretely. I like it, but it's everywhere. A lot of theorems reference it and use its results. For example, cool. So there's a lot more to it. Yeah. So what have we done so far in chapter 2? Section 2.1 dealt with the idea of getting really, really close to something. To find instantaneous velocity, for example. Right? That was 2.1. 2.2 dealt more directly with just the pure ideas of limits. 2.2 is where we had the graphs of things to look at. Cool. So that's what's going to be on this next quiz on Monday. It's going to be stuff from 2.2. They give you a graph and they ask you what's the limit as x goes to 2 from below and all that kind of stuff. Right? Are you guys with me? 2.3 is where we brought the algebra stuff in. And we said, can we compute this stuff algebraically instead of just relying on the just looking at it? There's got to be a better way to do it algebraically, and that's where we did the factoring stuff, multiplied by the conjugate stuff, right? Putting the fractions together, that kind of stuff. Okay. So that's going to be on the next quiz also, right? 2.4, we made everything really formal in this proof format, right? We got really, really deep into the idea of what it means to be close, because that's a big idea about limits. And then 2.5, we took the next level of limit is continuity. Right, 2.5 just says, not only does the limit have to exist, what else has to happen to be continuous? The limit exists at a for a function, and so it looks like, so the limit has got to be L at a, but f of a also has to be L. There you go. If that's true, then the possible hole was filled in, it's continuous. I can drive my car and not even worry about it. All right, I like it. Some potholes, but still we go. So, all right, that kind of catches us up to 2.6. 2.6 brings in the idea of limits at infinity. I like that. I like the phrase at infinity. So, for example, the limit as x goes to infinity of 1 over x let's say, well, doesn't matter. What would that be? Yes, I love it. Please, dear God. Is everybody cool with that? That's a very fundamental fact from pre-calc. I'm going to remind you about some stuff from pre-calculus. This is definitely going to be 0. Because, and never, please, never write something like 1 over infinity. Never write that. Maybe if you put in parentheses, because we very often put like 0 over 0, infinity over infinity. Those are indeterminate forms. But you can't put infinity into something, right? That would say you can get to it, you pick it up, and you put it in somewhere, and that's some neat shit. So what I told some students who had a big problem with that, I said, well, put 1 over BFN. Big freaking number, right? If you need something to kind of think about and look at, do that. Because you could put a big freaking number down there, right? How big? Big. Right? Not infinity, because you can't put infinity anywhere, because infinity isn't a thing. It's a process. So how do you put a process into something? You don't. All right, anyway, is everybody kind of with me? It's the same thing as saying, graph x equals 2, and I have some, or x greater than 2, and I have a student do like this, and they put infinity. I'm like, holy shit, what the? So what's this? I don't know, man. Gotta take the right kind of drugs to get there. All right. I'm not sure what that would be. So one way to have, how do I say this? Well, let's do this. Let's recall from pre-calculus. Recall something from pre-calc. If I have a rational expression, a rational expression like, for example, x squared minus 1 over x cubed plus 7x minus 2, right? There's an example of a rational expression. A rational expression is officially polynomial over a polynomial. I like it. If I have that, there are 3 cases for possible horizontal asymptotes. Does this sound vaguely familiar? Where do vertical asymptotes come from for rational expressions? Yes, because vertical asymptotes are the true walls. They say you cannot go here. Horizontal asymptotes, you can cross them. You can cross them an infinite number of times. They're just little things that say, oh yeah, come here eventually. Right? Vertical ones are like, you cannot exist here. That's my shirt. Right? You cannot go here. What are the 3 cases for horizontal asymptotes? Does anybody remember? And then I'll remind you about the very rigorous way of doing each of these. Yeah.
One of them when the denominator has a higher power.
Yeah. So let's say that what we're dealing with has f of x over g of x. Right. So if the degree of, I'm not sure, what did you just say? The degree, let's say the degree of f is less than the degree of g. What would that mean? If the top degree is less than the bottom degree. Who remembers what that means? Let me give you, that would be just like this. It should approach what?
0.
Y 0. And you're like, I don't know, I just remember. So yeah. So is the top keeping pace with how quickly the bottom's growing? No. If the bottom grows much quicker than the top, bottom bigger means whole thing smaller. So the whole thing's going to go to 0. A much more rigorous way to do that? Who remembers the rigorous way to show that? Divide everything by the highest power on your x. So divided by x cubed. Why am I allowed to divide by x cubed, by the way? Couldn't x be 0? Sure, but this is the limit as x goes to infinity. I only have to worry about values near infinity, which are very far away from 0. Is everybody, you're all like, I wasn't even concerned about that, but still, I got to say that. What do you get on the top then if I do that? One over x minus 1 over x cubed 1 plus 7 over x squared minus 2 over x cubed. And of course, the limit as x goes to infinity, what's happening here? All of these go to 0. As the bottom gets really freaking big, the whole thing is really freaking small. I'm dividing by bigger, I'm getting smaller. That goes to 0, that goes to 0, that goes to 0, that goes. So this goes to 0 over 1, which is 0. So in this case, the asymptote would be at y equals 0. The limit would be 0. Yeah, there's 0. There would be a horizontal asymptote at the x-axis, y equals 0. Does that sound vaguely familiar? Some of you guys have teachers that made you do this every time, and some of you guys had teachers that never showed you this. I kind of was in the middle, right? The degree of, what else could happen? What if the degrees are the same?
You take the coefficients.
Good. So let's do an example to see why. So what if it's x squared plus 2 over x squared minus x plus 1. If I divide again by the highest power I see, and again, I'm allowed to do that because I'm going very far away from 0. So that'd be 1 plus 2 over x squared over 1 minus 1 over x plus 1 over x squared. This goes to 0, this goes to 0. So in this case, I just get 1. If I would have put a 2 there, it would have been 1 over 2. That's why it's the ratio of the coefficients of the highest degree terms. Does this, yes?
Should it be as it goes to infinity or as it goes to 0?
Infinity. I always keep putting my zeros early, thank you. And of course, the last thing would be if the degree of the bottom one, let's see where we're at, is less than the degree of the top one. So this, the short answer here would be what? What's the limit as x goes to infinity for this one? Now the top is growing crazy fast and the bottom isn't keeping up. So if bigger, bigger, bigger divided by not as big, bigger, bigger, bigger divided by not as big. So the whole thing is going to go to infinity. Do you remember what this led to, though? It doesn't just go to infinity any way it wants to. It leads to the idea of some other kind of asymptote. Oblique or slant. I like it, depending on how formal your teacher was. I always like slant asymptote because it's like, add a slant. You could also have parabolic asymptotes, whatever, right? Because you do long division to figure out what the asymptote is. If these degrees are offset by more than just 1, then you're going to get different shapes of asymptotes. How we doing? Yes?
For part 2 of the horizontal asymptotes, if the coefficients were for the numerator like 3 and the denominator like 4, would the limit as x approaches infinity be 3 and 4?
Yeah, totally. If I put a 3 and a 4 there,
Okay.
this would have been a 3 and a 4 here, so this would have been 3/4. Those coefficients would be the only things left alive because they're the only things that have no x attached,
Okay.
right? So whatever they are, that's what the answer would be, the ratio of those two things. I love it. Yes?
So for the third property, or what it's called, how would you want us to write that?
No, I'll tell you this. The whole thing about slants and oblique asymptotes, that will come up, but if the question is purely a limit question, your answer is either going to be infinity or negative infinity, right? So for that example right there, if I look at that by itself, is it going to be positive infinity or negative infinity? Positive. I love it because the bottom is going to be positive for every value of x as you get to infinity, and the top is positive. Because who gives a shit about -1 when you're talking about 18 billion cubed, right? So this is going to be positive infinity. If I would have turned the top around, it would have been negative infinity. So it's one or the other one. I like it. Is that cool? No. Real quick, I want to go back to something I said earlier, and as long as you got my little graphic calculator up here, I want to show you. This is kind of cool. If I had this, let me see if we can make one that's not too freaky, over this. You don't have to do the long division, but if I did the long division, what would the highest degree be in the result? Just how far off are these? So it'd be an x squared. It should have an x squared asymptote. So somehow that the shape should start to become a parabola at the edges. So let's see what this thing looks like. If you're not here today, too bad. I don't feel like going over there. X to the fourth minus 1 parenthesis divided by x squared plus x. What did I say? Plus 1. Doesn't matter. See if I made this big enough to capture everything. All right, well, that's pretty obvious. If I do y equals x squared, and I make my window, I'm going to look up a little further on my y-axis. All right, this is good to do. That's the function. And there's the parabola. I mean, it's following that sucker right now. Now, y equals x squared wouldn't exactly be what it is when you long divide this. There's more to it. But if I was really trying to be careful, I could make something that looks. It would, in general, it's got to do parabolic. It could do weird shit in the middle, and then it's got to be parabolic. That's the idea of asymptote at infinity, right? Eventually, it's got to start to follow that. Are you guys semi with me? Okay, I like it. So normally in pre-calc, you almost always just deal with straight line asymptotes, slant asymptotes. But they could be anything. Okay. Oh, good. All right. Now let me show you something that doesn't quite follow these. These are all dealing with polynomial ratios. So what can I do if I get something that's not polynomial in nature? The little shortcuts all deal with polynomials. What if I had this? Doesn't matter. Over.
Change the exponents to
All right, let me do it the formal way, and then I'll tell you the quick way to do these. This is actually exactly the same thing as what we were talking about earlier. What is the degree of the top? 1. These have the same degree. The answer should be the ratio of the coefficients. But let's do this the formal way. The formal way is that way of dividing by the highest power. Now be careful. What's the highest power x has? 1. Right? Square root of x squared is x to the first. So if I divide this by x, now what's wrong with me dividing this by x? Can I actually get that x in there? Can I divide square root of something by something? No. So x is also known as the square root of. X is the square root of. Now, I don't know if anybody's having detail problems. We're going to positive infinity, so all my values are positive. Don't overthink this if that's what's happening. X is the square root of x squared. Thank you. In general, the square root of x squared is really what? In general, not dealing with anything here. What's the square root of x squared in general? It's not x.
plus or minus x.
Sort of, but officially, not officially, what is it? Don't say plus or minus x because that's not true. The square root of 9, which is square root of 3 squared, is not plus or minus 3, right? Do you understand the distinction there? I'm not just being an asshole. I'm trying to, right? You're like, oh, you are being, but a little bit. I've got to be a little more specific here. That's not the answer. It's not plus or minus. It's got to be positive, doesn't it? And what makes everything positive? Absolute value. Why I'm not concerned about that? Because I'm using positive values for x, right? Okay, so there's a lot kind of going into this, but the look from above is not that hard. It's the same thing we were doing before. I want to divide by the highest power. I just have to make this one square root of x squared. So I am dividing by the same thing. I am following the rules of fractions. I'm doing the same thing to the top and bottom, right? So now what does the top become? Square root of 2x squared divided by square root of x squared is 2x squared divided by x squared is 2. 1 divided by x squared is 1 over x squared. And then you get 5 minus 3 over x. Is that decent? This is funny. This is like Jeff finding out all the people he does not want to play poker against. This is so true. What, all right, what's going on, everybody? Help me out. So if I write this down, where is it? I don't know, is that better? That's what these are the same thing. Is that cool? These are the same thing. I'm just seeing if that's better, because now you can just see how those cancel. That's 1 over x squared. Okay. So you get the square root of 2 plus 1 over x squared over 5 minus 3 over x. And what's that become? That goes to 0. That goes to 0. So what am I left with? Right, 2 over 5. Which, if you look back, what is the coefficient of the x term, rad 2? What's the coefficient of the x term down here? 5. It's the same rule. It's the same exact rule. Just have to be careful about the root that's being taken. Okay. All right. What about this? Ooh, yeah.